welcome to the separation process in gas chromatography. So we've already talked about chromatography or chromatographic separations in chapter 22. We've talked about the theory of it. So here we're going to talk about only those applications towards gas chromatography. And then in chapter 24, we're going to talk about the applications to liquid chromatography or high performance liquid chromatography, HPLC. So in gas chromatography, the analyte is transported through the column by the gaseous mobile phase called the carrier gas. And in gas liquid partition chromatography, then the stationary phase is a non-volatile liquid that is bonded to the inside of the column or to the outside of solid support particles. So here we have a cross-section of a capillary column or an open tubular column. We've got the central region in here in white, and that's where the carrier gas is transporting our solutes through. We've got this outer gray circle, that's the column wall, and then this lighter blue circle coating the inside of the column wall, that's where our stationary phase is. And so our solutes are equilibrating between the gaseous carrier gas in the center and that stationary phase coating that outer wall. On the other hand, in gas-solid adsorption chromatography, that stationary phase is a solid and the analyte molecules then adsorb directly onto the solid surface. So we've got some solid particles here. This is the bluish blob there. And our solutes, these gray molecules, are then sticking directly onto the surface as the carrier gas flows past. So here we have a schematic of a very simple gas chromatograph. A volatile liquid or gaseous sample is injected through a rubber disc called a septum over here in our injector port. And note that that injector port is heated to keep our sample in the gas phase. So if that sample is a liquid, it then quickly absorbs heat from the injection block and it then rapidly vaporizes. That sample vapor is then transported down the column by the carrier gas, which is usually helium, nitrogen, or hydrogen. And as those vapors travel down our column here, then different analytes are separated via their interactions with that stationary phase. And then our separated components exit the column and they're passed to our detector here, which then outputs some signal to generate a chromatogram. They're usually displayed on a computer. Now the column here is heated by the column oven because it must be kept at a high enough temperature to provide an analyte vapor pressure high enough for that analyte to move down the column within some reasonable time frame. We don't want that analyte vapor condensing on the column and then just sitting there. We want it to be spending a lot of its time in the gas phase and partitioning back and forth between the mobile phase and the stationary phase so that it gets separated from the other components, but so that it doesn't sit on the column forever and take hours to come off that column. The detector also has to be heated, so it's heated by our detector oven over here, because that detector has to be at a temperature higher than that of the column in order to prevent condensation of our analyte within the detector. If our detector temperature is lower than the column temperature, then some of the analytes that come out of the column may then condense inside our detector. So most of the time, the column is a narrow, open tubular column called a capillary column. And that column is made of fused silica, so SiO2, and coated with polyimide, which protects the silica from atmospheric moisture and provides support. And so you can see here, we've got our outer wall of the column, we've got some stationary phase coating that outer wall, and then our carrier gas is flowing past. And generally, these columns are long enough that we coil them around in a spiral like this. So as we saw earlier in section 22.5, these open tubular columns or capillary columns provide a higher resolution, shorter analysis time, and greater sensitivity than packed columns do. But the downside is that they have a smaller sample capacity. So the capillary column is going to be useful for an analytical separation where we're trying to take a measurement or determine what we have in our sample. They're not going to be good for preparative separations in an industrial process where we need to separate out a large quantity of one component of a mixture from the remainder of the mixture. So So we have a few different ways of arranging our stationary phase within the column. And they are the wall-coated, support-coated, or porous layer. A wall-coated column has a 0.1 to 5 micron thick film of liquid stationary phase coating the walls of the column. So they're coating the column, and this is what we've seen thus far. A support-coated column has solid particles affixed to the column walls, and so those are these open circles here. And then onto those support particles, we have liquid stationary phase coating the surfaces of those support particles. So the liquid stationary phase is still the blue circles here, but now we have a greater surface area here than we had on the last slide, because now we have a greater surface area on those particles than we have on the column wall. And our last type of column has a porous layer column where we have solid particles that are themselves the stationary phase. And these porous particles have a much higher surface area than the column wall does, and thus the column can handle a larger sample volume. So our analyte can actually diffuse into these solid particles at least some distance. So the inner diameter of our column is typically between 0.10 and 0.53 millimeters. The length of the column is usually between 15 and 100 meters, with 30 meters being the most common. And a narrower column offers higher resolution than does a wider column, but will require a higher operating pressure and have a lower sample capacity. So recall that the number of theoretical plates, N, capital N here, on the column is directly proportional to the column length. And also remember that the resolution is proportional to the square root of N, the number of theoretical plates on the column, and thus the resolution is proportional to the square root of the column length. So increasing the thickness of the stationary phase increases the retention time and the sample capacity of our column. It also increases the resolution of early-eluting peaks with a retention factor of K less than or equal to 5. And these thicker films of stationary phases can shield the analyte from the silica surface and reduce tailing. However, they will also increase bleed, the decomposition and evaporation of the stationary phase at higher temperatures. The stationary phase is chosen based on the principle of like dissolves like. That is, nonpolar solutes are separated best in nonpolar columns, and polar solutes are separated best in polar columns. And then solutes with intermediate polarity are separated best in columns with intermediate polarity. So we can even separate optical isomers using a chiral stationary phase. Now, as the column ages, that stationary phase can be lost, exposing the surface silanol groups. So this is the silicon, oxygen, hydrogen group. And tailing of peaks becomes worse. So to reduce the loss of stationary phase, we usually bond the stationary phase to the silica surface and cross-link it to itself. And when we say bond here, we really mean covalently bonded to the silica surface. So the column should be periodically checked with a standard with known retention factor, number of theoretical plates, and peak symmetry. If you find that you now have a different retention factor or number of theoretical plates or an asymmetric peak, then you know that your column is being degraded and it might be time to replace that column. So, at higher operating temperatures, that stationary phase can decompose, which causes bleed of decomposition products from the column. And this bleed increases the background signal in most of our detectors, and thereby it reduces the signal-to-noise ratio. So column bleed can be minimized by using the thinnest possible stationary phase and the narrowest and shortest column that provides adequate separation of the components of your mixture. And we also must avoid oxidation of our stationary phase by O2 in our carrier gas. So high purity carrier gas should be used and should be passed through an oxygen scrubber before entering the column. Even a 1 part per billion concentration of oxygen can degrade the column over time. Water vapor can also degrade that stationary phase via hydrolysis. So the silica surface is typically modified to remove the silanol groups, those SiOH groups, with which the water vapor can react. So recently, ionic liquids have come into use as a stationary phase. And these liquids melt at the low room temperature and have a low volatility at elevated temperature. And then, of course, because they're ionic, they have very high polarities. In packed columns, the stationary phase is either a non-volatile liquid coating the surface of fine particles, the support, or the surface of those fine particles themselves. Now remember that packed columns allow for larger sample volumes than the open tubular columns do, but provide broader peaks, longer retention times, and lower resolution. Packed columns are useful for preparative separations used in industrial applications and for separating gaseous analytes that are poorly retained. Now, packed columns are typically made of stainless steel or glass. The typical column length is between 1 and 5 meters. A typical column diameter is 3 to 6 millimeters. The solid support is often silanized silica, which has reduced affinity for the polar solutes. Now, decreasing the particle size in our packed column decreases the time required for solute equilibration, and thus it increases the efficiency. However, the smaller particles pack together more tightly, and that means that we need a higher pressure to force our mobile phase through the column. Now, the particle size in our packed column is expressed either in microns or as a mesh size. Now, mesh size refers to the size of streams through which the particles are passed or not passed. So the mesh number is the number of openings per linear inch of the screen. For example, a 100-200 mesh particle passes through a 100 mesh screen, one in which there are 100 openings per linear inch, but not through a 200 mesh screen. So let's examine how the relative retention times of polar and nonpolar solutes change as the polarity of the stationary phase changes. So here we have two chromatograms. We've got chromatogram A and chromatogram B here. So in chromatogram A, the stationary phase is nonpolar. And you can see we have a bunch of peaks all bunched up together there. These 10 compounds are removed largely in order of increasing boiling point, and you can see the 10 compounds are over here with their boiling points there. That is, the primary determinant of retention on the nonpolar column is the volatility of the solute. On the other hand, in chromatogram B, over here, the stationary phase is strongly polar, and the strongly polar solutes are retained longer. And note that our 4 alkanes are eluted first, followed by the 3 ketones, and then the alcohols are eluted last. And that's because the alkanes are the least polar, those are the most nonpolar, then the ketones are of intermediate polarity, and the alcohols are the most polar. And that occurs because the hydrogen bonding to the stationary phase is the strongest determinant of retention, followed by the dipole-dipole interactions. And since the alcohols will exhibit hydrogen bonding, they have the greatest retention times. Since the alkanes will not exhibit hydrogen bonding or dipole-dipole interactions, they have the shortest retention times. And since the ketones will not exhibit hydrogen bonding, but they will exhibit the dipole-dipole interactions, then they have intermediate retention times. So the Cobat's retention index I for a linear alkane equals 100 times the number of carbon atoms. So for octane, I is 800. For nonane, I is 900. So if we look at some chromatogram here, we've got octane there, and we have nonane here, and we've got some unknown peak in the middle. That one is the peak that we're going to be looking at here. So that compound that elutes between octane and nonane has a retention index given by this equation here, where the lowercase n, there and here, is the number of carbon atoms in the shorter alkane, so octane in this case. The uppercase n, there, is the number of carbon atoms in the longer octane, so nonane in this case, and the Tr prime with I in parentheses is the retention time of I, so this is the unknown, the shorter alkane or the longer alkane. So in this case we have the retention time of the longer alkane. In this case, we have the retention time of the shorter alkane. In this case, we have the retention time of our unknown. Often, gas chromatography is run using temperature programming, in which the column temperature is increased during the separation to increase the analyte vapor pressure and decrease the retention time of our late eluting components. Now, to maintain the resolution of early eluting peaks, there is often a constant low temperature period at the beginning of the program. Similarly, pressure programming can be used to increase the pressure later in the run to increase the flow rate of the carrier gas. Now, the advantage of pressure programming over temperature programming is that at the end of the run, the pressure can be quickly reduced to the initial pressure for the next run. On the other hand, with temperature programming, we must wait for our temperature of our column to drop, and the column and column oven will have a significant heat capacity, so it's going to take a while for that temperature to drop and then stabilize at our initial temperature for our next run. Furthermore, the pressure programming can be used on temperature-sensitive analytes that will not tolerate the higher temperatures that would be used in temperature programming. So now let's talk about carrier gases. The most common carrier gas is helium because it is compatible with most detectors. With a flame ionization detector, nitrogen provides a lower detection limit than does helium, and thus the nitrogen should be used instead. Now, the nitrogen, helium, and hydrogen provide the same minimum plate height at different linear flow rates. That is, if we look at the Van Deemter plots, we see here we've got a curve for nitrogen, here in black we've got the curve for helium, and in blue we've got the curve for hydrogen. And you can see that they're all reaching the same minimum plate height at different flow rate. So we've got our plate height there and linear flow rate or linear velocity along the bottom. And this means that if we're using hydrogen, we can operate at a much faster flow rate than if we're using nitrogen. And also note that the shallow slope for hydrogen at high linear velocities, so over here, means that we can operate at flow rates significantly higher than the optimal, so much higher than that value in there, without a significant loss in resolution. Whereas if we're working with something like nitrogen and we double the flow rate, we're going to significantly change the resolution. We can double the flow rate from, say, 30 centimeters per second up to 60 here, and we won't have changed the resolution by a whole lot, but our analysis time will drop significantly. Now, naturally, hydrogen can be dangerous because hydrogen concentrations in air of over 4% are explosive. Now, in the past, hydrogen use was fairly limited, but the small volumes involved in capillary chromatography mean that the dangerous concentrations of hydrogen are unlikely to occur. High purity hydrogen can be generated using an electrolytic generator, thereby removing the need for a tank of compressed hydrogen. So the reason that helium and hydrogen provide better resolution than nitrogen does is that solutes diffuse more rapidly through the lighter gases. And this reduces the equilibration time and thus the mass transfer term, that C term, or the CUX term, in the Van Deemter equation. So here we have 3 chromatograms obtained with our 3 different carrier gases. We've got nitrogen here, and you can see that those 2 peaks are not well resolved. When we move to helium, they're better resolved, and when we move to hydrogen, they're even better. Now, to shorten the analysis time, most analyses are run at flow rates 1.5 to 2 times that optimum flow rate. And so effectively, we get much faster analyses in return for a slightly lower resolution. That is, we choose the flow rate that provides the maximum efficiency, so this is the most theoretical plates per unit time. And this now brings us to guard columns and retention gaps. A 3 to 10 meter guard column is often placed between the injection port and the capillary chromatography column. That guard column is an empty capillary column whose walls have been silanized in order to prevent solute retention. And the purpose of our guard column is to accumulate non-volatile substances that would otherwise contaminate our chromatography column. That guard column can be trimmed periodically in order to remove those contaminants. Alternately, we could simply replace the guard column in its entirety without having to replace our chromatography column with our stationary phase in it. Now, a retention gap is physically identical to a guard column, but its purpose is to improve peak shapes under certain conditions. So if a large volume of samples, so larger than 2 microliters, is injected using splitless or on-column injection, which are described in section 23.2, then microdroplets of solvent can persist inside the column for the first few meters. And these microdroplets of solvent can carry with them the dissolved solutes, which then carries them farther ahead of where the solute might be if it's being retained by the column. But on the analytical column, these solutes would not be retained as long as if the droplet had evaporated immediately upon injection. And thus, the droplets will give rise to solute peaks at different retention times from the main solute peak. And so effectively, the retention gap provides a few meters of non-retaining column in which the microdroplets can evaporate. Now, when we're calculating the number of theoretical plates, N, or the plate height, H, do not include the length of the guard column or the retention gap with the length of the column. That capital L that we're using there is only the column that contains that stationary phase. So the column length L there refers to the length of the column in which the solutes may have different retention times. And that was the separation process in gas chromatography.